In this lecture, we're going to discuss the effect of fluctuating stresses in the fatigue calculations. Last time we considered uniaxial stresses that were fully reversed, and this time we're going to talk about fully reversed stresses as well as multiaxial stresses. So we've moved to category 3 now. So let's have a look at the problem statement. If our problem statement includes things like forces and the number of desired cycles, what our material is made out of, and the geometry and shape of our part, then there's going to be two phases to solving the problem. In the first phase, we'll do a free body diagram, we'll find loading diagrams, we'll find the location where the maximum stress occurs. If there's more than one location, then we'll consider all of the locations and find the maximum stress. And then from there we can find the maximum stress state. And then we can find the von Mises effect of stress, and we need to do that if it's a multiaxial stress. If it's a uniaxial stress, then the von Mises effect of stress is the same thing as the maximum stress. So that's one half of the problem. We also can take our given data about the materials. So the ultimate strength, fatigue limit, the endurance limit of our part, and we can find all of our knockoffs. We can calculate a modified endurance limit, and we can calculate SM for 1,000 cycles, and from that we can get the number of cycles that we expect. Using the number of cycles, we can get the strength at that number of cycles. So from the first half we have our sigma A prime. This is the von Mises alternating stress. We have our strength at that number, at a given number of cycles, and the ratio between the two of them is going to be our factor of safety. So that's fairly straightforward. Well, what happens now if we consider that the alternating component is not the only stress component, that there is a mean stress as well? So this is the graph we've been looking at so far, and what we see here is on the x-axis we're graphing number of cycles, on the y-axis we're graphing the strength of the material. The other important graph to consider is this one, and if you notice on the x-axis we are graphing the mean stress, and on the y-axis we're graphing the alternating stress. The cases we've considered so far reside only on this line right here where the mean stress is equal to 0. There are several different theories. We'll talk only about the modified Goodman. Just as in passing, the Gerber parabola actually conforms to data better than the modified Goodman, but the modified Goodman is a good one for calculation, so it's the standard line, and since it's more conservative than the Gerber, it's considered the one to use. The Soderberg line is no easier to use than the modified Goodman, and it's extra conservative, so in general we don't use this line. Now we need to consider what this other line right here is, this yield line. So let me show you, as we dial into this a little bit more, we need to think about what's going to be happening. In general, when a part fails, if it's all alternating, we're not considering yield because it doesn't fail in a yielding fashion. It fails as if it's brittle. If there's all mean, and this means it's not an alternating problem at all, then we're going to consider failure to happen at yield, especially for ductile materials that have a significant difference between the yield strength and the ultimate strength. And so this cutoff line shows me the effect as I begin increasing the amount of alternating load relative to the mean load. I begin decreasing, this line is going to travel all the way up to the yield strength graphed on the y-axis. Let me zoom out and show that a little better. In this line you can see the yield strength is going to be a lot higher than our adjusted endurance limit or fatigue limit. And so this line right here is only valid for the places as a criteria, will only be valid as a criteria when it's less than the modified Goodman line, which starts at the endurance limit and goes to the ultimate strength of the material. And this line is given by this equation right here, and this is going to be the important equation going forward. If there's compression, we could come back to this augmented modified Goodman diagram and calculate everything we need to from the compression side as well, but I think it'll suffice as an explanation just to consider things happening in tension and what's going on, or at least in even materials. This graph is only good for infinite life. If I have finite life, what that means is that I'm slowly moving up this curve all the way until, if I'm only going to be operating at one cycle, I'm now at the yield strength up here at the top as well. So this is one graph of many. This one shows either infinite life, or if we're talking about the fatigue strength, then we can talk about it as being 5 times 10 to the 8th, or wherever the fatigue data is given. Let's take a look at a 3D image of these two graphs projected onto each other. As you can see, as I look this direction, I see number of cycles on the x-axis and the alternating stress on the y-axis. That is our SN diagram for only alternating stress at this end. Looking from this direction, if I'm all the way out at infinite life, or at 5 times 10 to the 8th, or the farthest out as I can go, this is where I got my numbers for the modified Goodman graph. And what we see is that as we move, as we do any cross section, so at any given sigma m, there exists two sets of curves. There's going to be, if I'm looking at sigma m, as the mean stress increases, my projection of those lines are going to start decreasing. So as this graph goes higher, as I move from sigma n equals 0 all the way to sigma m equals the ultimate strength, on this graph, these lines are cross sections of that 3D surface, and that's what they're going to be doing as I move, as sigma m gets larger. As number of cycles go up, if I'm looking at this graph has the highest number of cycles right here at the bottom, and the lowest number of cycles right here at the top. This lowest number of cycles right here of one cycle corresponds to this portion of the graph, and the highest number of cycles right here corresponds to this portion of the graph. And so we can see the two of them are connected to each other. So how do I find a factor of safety? And again, I'm going to start with considering what's happening at the infinite life, or at the fatigue limit. This is the modified Goodman line, and we're given some sort of stress state where there's a mean stress and an alternating stress at this location here. And the question we have to ask ourselves is, when extra weight or extra stress happens, what does it look like? In case 1, we're going to consider the case where the alternating stress is a constant, and we're not going to be concerned that it ever increases, but the mean stress might increase. If that's the case, my factor of safety is going to be the ratio of this line yz to the total line yq, and that equation is given here. Another condition would be to consider that the mean stress is going to stay still, and if there's any increase, we're going to see it all in alternating the alternating stresses. If that's the case, our factor of safety now will be xz divided by xp, and that equation reduces to this. The third case, and maybe this is the most common to consider, is that the ratio of sigma m to sigma a remains constant. In other words, if I have any more alternating, I'm also going to have more alternating mean. And so now my factor of safety is going to be OZ divided by OR. And it takes a little bit of work, but we can get a factor of safety that reduces into this form. The final possibility is that we have no idea what's going to happen. Maybe only sigma A increases, maybe only sigma M increases, maybe the ratio increases. And so what we're going to do is we're going to draw a circle. And the first circle that touches any of these lines will be the location of the minimum stress for failure, and then we'll find a ratio of that projected distance, the radius from where I am to whatever line was closest. And now we'll consider OZ divided by this total length. OZ, and so that's what we've got. OZ plus ZS divided by OZ. Now OZ is not too hard to figure out, but the term for ZS is a little more complicated than I wanted to put on the slide, so you can look to the book. In general, if I don't tell you any differently, in this class we're going to assume that if there's a varying load, it's going to be varying in the format of case 3, where the ratio remains the same. Okay, so let's take a look now at this fluctuating loading condition as compared to the fully reversed loading condition. I still have a problem statement, still the same: forces, number of cycles, geometry, material, all of that's given. The top half remains identical. I'm going to find the strength for the number of cycles that I'm looking for. The bottom half, and so I'm still going to get my Sn out. The bottom half starts off the same all the way until we get to von Mises stresses, but the problem now is that von Mises stresses have two components. They have an alternating and a mean. Then I'm going to plug both of those into my modified Goodman criteria, and out will come a factor of safety, and this will be the answer I'm looking for, the factor of safety. There's another way these types of problems are often asked. Suppose my problem statement is I'm given what my factor of safety is desired to be, and I want to know with this particular geometry how long will the part last. If that's the case, I'll solve the bottom portion here just as before. I'll get my von Mises effective stresses for both alternating and the mean. I'll take my factor of safety and use that to compute now what my strength will be. Now notice I don't know N. I know what the strength desired. If I have this strength, then it'll have this factor of safety. And then I can take this strength and then start my top half, and I've got all the way down to Sm, and now I'm going to solve rather than for Sn as I've done in the past, but now I'm going to use Sn to find the number of cycles in this equation, which is the one that's S is equal to A times N raised to the B, as we talked about before.